All right. Calvin, cheers. Would you like to introduce yourself?
Yeah, very excited to have Jaehun with us today. He is, I guess, close to finishing his PhD at UW with Jaehun. He's also part-time at NVIDIA. He's been doing a lot of data work, both in selection and synthesis of data. He also wrote the Impossible Distillation paper, which we've talked about a few times. But today he's going to talk about synthetic data generation, how diversity matters, and reasoning. So very excited to hear from you. And
Yeah, thanks for inviting. Nice to meet you all. It's a great office. I like the height of this office and the name of the of course. I'm honored. Yeah, so I'm glad to talk about our recent gigantic project on this gigantic agenda of understanding the data diversity. So I'm sure you guys are all pretty much well aware of all these limitations I'm gonna make it for you. So if we want to improve and analyze specific capability measured by some benchmarks like say Hendrix math, we all know what the best shortcut these days is. If we have, so long as an access to a good model already capable of these solving these kind of tasks, then all we need to do is just prompt these models to, generate some, give them some problems and solutions from the seed samples, and then generate more like this, and then we'll take the outputs as this type data, consisting of problems and solutions. So simple as that, but we all know it's been a go-to method from many of the, especially open source communities, because it's a shortcut to follow up with what proprietary models. So long story short, the promises of synthetic data looks like this. So we start from a strong inner feature model. And then we'll sample some data from the feature model's distribution, basically a little moderated, let's say, the distribution that focuses on the specific capability that we would like to maximize. And then importantly, we're going to filter those data based on, say, some heuristics like correctness. And then we train on sample data, which will lead us to a next generation model, hopefully better than what we started with. So the promise here is that if we keep this loop running, we're going to improve the model, which we call in fancy terms like iterative refinement, self-improvements. But you guys might have experienced this, but turns out it's not as simple as that many of the times. So one example of this bottleneck we have experienced is what we used to call Amazon rainforest trap. A good example was when I was trying to generate some classic NLI data set. NLI is like it's a classic NLP task where it's pretty simple. We have a classification task where the input comprises of two text snippets, premise and hypothesis. We just want to infer the relationship, logical relationship between the two. So in this example, the premise, we want the model to correctly classify that the premise entails the hypothesis. So yeah, the straightforward way of solving this by generating synthetic data would be something like this. We start from the seed data set that has been annotated by, say, humans already existing on Data Hub. And then we're going to sample some future examples to curate, diverse input prompts, generate something similar to these, and then we're going to prompt a strong model. But here the interesting thing is, it really depends on which model we're using for data generator. But in case of GPT-4o, it really loves to talk about Amazon rainforest when it's generating these samples. So this is actually quite, it's protruded because if the prompt has nothing to do with, say, environment and whatnot, it just loves to talk about Amazon rainforest. In fact, GPT-4o talks about Amazon rainforest in 34% of the generated samples, no matter what future example. Yeah. So yeah, well, at this point, you might think if this is just about lack of topical diversity, we can artificially fuse it right, by engineering the prompts, like sourcing some of the keywords from the web, and then putting it into the model to explicitly include these keywords when generating the samples. But turns out, oftentimes, for tasks which requires a little more sophisticated reasoning, say generating synthetic math problems, the problem is the lack of diversity could be secretly happening because these generated problems could be similar, even when they appear to be very different in terms of their surface forms. So these actual two examples are generated by GPT-4 when we gave it JSMAK as the seed sample. And you can see that immediately the problems themselves seem to be pretty different from each other. But if you actually try to solve them, we humans can understand that the skeleton solutions for solving these problems, the templates are essentially the same with different numbers. The problem here is it's really hard to detect these kind of tasks, cases. So sample A and sample B are the ones from the previous slide. So you can see that sample B is essentially different looking compared to sample A, but it does involve a similar reasoning. So essentially, it's an equivalent problem. We introduce another problem here, sample C, which has a lot of token overlap with sample A. It talks about some guy named Bill and walking to somewhere. So it's pretty similar in terms of their surface form. But if you actually solve the problem, you'll realize that it's a completely different problem with different haplogroups. But concurrent methods for measuring the diversity of the samples, like say token overlap or semantic similarity using embedding cosine similarity, they always say that sample C is closer to sample A, meaning that it does not really capture what matters in terms of diversity when you're solving these tasks. So yeah, the myth of diversity is like this. We all know that high quality data isn't just about collecting more correct data. Of course, collecting correct samples is important, but it doesn't really fully explain why one data set of similar quality and scale generalizes better than the other. And we know that data diversity is an important dimension to explain this, but there's no principal way of measuring them. There are some measures, but they are oftentimes heuristic, like relying on lexical diversity, topical diversity, or they are often task specific, like measuring the diversity of summarization strategy, whether they are abstractive or extractive, when we are trying to specifically measure the diversity of summarization data sets. And we don't yet really know what these heuristic diversity definitions really have to do with the actual model performance trained on these data sets. So the first goal of this project is to provide a principle, one of the largest scale analysis, focusing on these diversity measures. So to do this, we define the desiderata of good data diversity measure like this. So when we have two data sets, D1 and D2, of comparable size and quality, a good diversity measure F should satisfy the following. So if D1, one data set D1 is more diverse according to F than D2, and when we train the same model on D1 and D2, and D1 trained on D1 should be generalizing better to out distribution than D2. There are a lot of underdefined terms here, but I'm going to explain what these are actually implemented in the later slides. But towards this desiderata, we define our own measure called G-Bandy, which is essentially measuring the entropy of the data set in a gradient space. So the high-level intuition behind using gradient information and entropy of the gradients is like this. So gradients, so long as we're training these models using the gradient descent, intuitively you can say that gradients kind of represent the knowledge attainable from each of these samples in the data set, which means that if we have samples with diverse gradients, then if you train a model on that data set, it will hopefully generalize better to, say, unseen domain or out of distribution in that task. So yeah, what we do in G-Bandy is literally this, measuring and representing the data samples with gradients. So given we have, say, input and output, X and Y, which is the most generic form of L1 fine-tuning, we literally measure the loss gradients using a small proxy reference model. Specifically, we use the Q1 0.5B instruct model. So in order to measure this gradient based on negative low likelihood of Y given X. There are some details, but distilling all of those details, the problem here is that even with this small reference model for gradient computation, it's too large because basically, even if you use 0.5B model, this means that we are representing each of the data sample as 0.5 billion dimensional vector, which is intractable. So what we do is we're going to do off-the-shelf dimensionally reduction technique called Rademacher random projection, which is actually pretty simple, but which allows us to significantly reduce down the dimension to say 1024, while providing this guarantee that it preserves dot products between all these gradient vectors. And we earlier we mentioned that we were just going to measure the entropy of these data sets, meaning that we only are interested in the relative distances or similarity between these gradient vectors. All we need is the preservation.
Sorry, you said this, but you said you used 0.6 for this?
0.5.
Yeah, 0.5. Okay. So you're taking the 500 million
Exactly.
gradient vector.
Yep.
And that's
Quanting it down
at 1024.
Exactly.
Okay. And does Rademacher projection provably maintain the distances?
With high probability.
With high probability. Okay, got it. Cool.
I actually was I wasn't sure about that, so I actually tested it when I was implementing this. Yeah, I was surprised. It's actually pretty simple. The Rademacher projection is just multiplying by a random matrix where each of the entries are -1 or 1. Simple as that, but it does provide this kind of statistic here. So yeah,
You're doing a projection from billion to 1,000?
yeah.
The high probability parameter is a function of the projection size. So the billion to 1,000 is a huge compression of.
Well, yeah, it is. But if you
So,
think
like-
about like how embedding works, like it also somewhat makes sense because like the space of possible text token combinations are like infinitesimal, but we still kind of represent it using very low dimensional kind of a factor, right? 1024 AK. So yeah, I think in that sense it kind of also makes sense that the gradient information mostly can be represented via like relatively small projection. Yes.
Do you, maybe this is later, but have you compared dimensionality reduction of like the gradient information versus just using representations as
Representation in
like intermediate
embeddings, stuff like that.
representations?
Yeah, we did.
Also, like, did you consider this like last layer or middle layer representation versus like a random outcome?
I see. Well, I didn't do like a thorough comparison of that, but I did try using like specific layers or specific components like MLP, gradients with respect to MLP and whatnot. But like it didn't really make that much of a difference. Like it's using specific. Maybe that's because I didn't do like thorough comparison between those components. And the problem is like even if you use a specific component, it still is a huge dimension. Like yeah, so because you can't really choose a specific layer, like
Yeah.
layer 20 MLP or stuff like that, right? So
Right.
yes.
But if you could get like the last layer or second last layer, the backward projection is much cheaper. Like you don't have to backward project throughout the model.
Right,
So that
right.
is enough.
Yeah, that's actually a good point. I haven't tried using like a specific higher layer information, but maybe that could reduce significantly the connection perhaps. But maybe preserving most of the
You said using all the parameters versus
All
using
parameters.
just the MLP weights or gradients versus just using the attention gradients was roughly the same.
roughly the same. Probably because like most of maybe the information in the gradients are sparse. So maybe they're already in one specific component. So if you just even if you choose one of them, it's
Sorry, so before you do the dimensionality reduction, are you normalizing like sample wise all the gradients first?
yeah.
So like
Yes.
you're kind of losing information about the loss.
Right.
And I wonder
The
if
scale of the
that
loss.
affects like, yeah, I don't know if that's.
Yeah, that's actually a great
dimension you
point.
wanna
So what we
retain.
have found is that these y in the Allen fine-tuning scenario is variable length, right? So
Yeah.
it's kind of I have found that it's quite perturbed easily by the scale of the loss is really subject to the length of the outputs and whatnot. So originally I have used unnormalized gradients, but first of all, it's computationally very unstable. Second, the reason is the length of we wanted to remove the effective length, like affecting too much. So I think many of the existing works on data attribution and whatnot, also using the gradient information does the same thing, like normalization prior to projection or whatnot. So
I have a question.
Yeah.
So the gradients that are computed using the smaller model.
Right.
What if it's noisy? What if they're like ambiguous or adversarial examples? Would that create like sparse clusters in a embedding space?
Sorry, I didn't get that question.
What if you had like certain low confidence examples? So when you
Right.
compress that into a
Right. So I think good thing about this is that we don't really need a already capable model to compute the gradients. I think it's not about that because like we have done a ablation study on like the actual gradient proxy model, and even with non-instruction tuned based model with the 0.5p scale, it kind of works okay. I mean, it's worse than instruction tuned model. So I think the model does not have to be like well aware of how to solve these problems or whatnot. Probably because of the fact that the Y already has that information, like the actual graphical solution to the input. So yeah, even if most of the time the model wouldn't know how to correctly solve this problem, but that doesn't really affect the quality of relative diversity.
Yes, I have another question. You said you chose the instruct model.
Right.
I'm actually curious why that versus the base, because for gradient to work, you actually want the example to still be learnable, then it says gradients. But instruct model potentially already saw math and the grades are saturated. So would it have been better to use the base model, which actually learns more and has directed gradients?
Right. I guess like if it's just about general instruction tuning, that would make sense. But here, what we want to measure is like relative diversity of, say, math reasoning, right? So like the differences between these information from these different samples are very intricate.
So I guess
Ideally.
if you want more granular things, then you want an instruct model. If you want more coarse.
Yeah. So the funny thing is like even if we use like a different instruction tree model, like not Quen, but like say Llama 3.1 or something, 1B. When one data set is diverse according to one gradient proxy, it tends to be diverse according to other models as well. Maybe it's because all the models are pretty much the same in that sense, because we are measuring the relative diversity. So but using instruction model clearly and consistently led to better results.
I have a question about your last point. So basically you're saying that like the family of model, like you can select with Llama and train for Quen.
Yes.
So like, I see that's pretty interesting because like there's no.
Right, that was
the
unexpected
gradient,
for us.
so you wouldn't expect them because the data that you.
The gradient should be completely different, but the maybe the relative entropy is pretty much consistent. Any other questions?
That sounds like a soft point in favor of the platonic representation hypothesis, but
Yep.
but like we are generally like the end goals for these models are generally the same, so I guess it's not super surprising.
Yeah, so what I just described is about representing each of these data points in the data set using gradient information. So it should be E times 1024. How are we going to aggregate these information into a scalar score? In order to do this, we introduced this Bandy score from Princeton, I think. So it essentially allows us to measure capture the notion of entropy in an empirical distribution without actually knowing the support of that distribution. So basically what we do is measuring the entropy of eigenvalues of normalized covariance. So intuitively, if this is low, it means that most of the variance between the data points are explained by one or two eigenvectors, like in PCA. So means that diversity is low, and vice versa when the score is high. It kind of follows our intuition that when the gradients are focused in a specific region, this should be low, well dispersed, and this should be high. So yeah. So recalling our goal of evaluating data diversity measure, we said that good diversity measure should correlate with how the model generalizes after training. Yes.
Can you go back?
On this slide?
Oh yeah. So this is the gradient, right?
Yeah.
But you're looking at the if the direction is the same but the magnitude is different.
It's
It would
considered
be
to be
at-
similar.
No, but it would be at different places, right?
Oh, I think yeah. I always had a thorny thought about this diagram, but since we are measuring
Okay.
cosine similarity, if they are in a similar direction but different scale, it should be punched into like
Okay.
basically the same thing.
Normalization also would
Yeah.
make that
Yeah,
beforehand.
it's bringing that.
Right.
Okay.
Yeah. So we did this correlation analysis by literally following this description. So what we do is we're going to prepare a large pool of data, and we're going to sample a lot of different train sets from this pool, and then train the same base model on each of the train set, and literally just analyzing the correlation between the model performance and the diversity of the train sets. So there are a lot of underdefined concepts here. So first of all, we said two data sets should be comparable size and quality, but how do you even define data quality, right? So what we did here is leveraging the strength of synthetic data because we have full control over the data generating function. So we use the basically same data generating pipeline, same LLM, same sampling strategy, same filtering strategy to generate the full pool of the data. So that we were kind of like evicting this issue of quality confounding. And the second point is how are we going to measure this perfectly out of distribution? So the most intuitive way of doing this might be, just collecting a lot of different out of distribution benchmarks and averaging the accuracy. But I have found that this is quite noisy because it basically does not account for the complexity of each of the benchmarks. So in math reasoning, this means that we're considering 3% performance gap in basic arithmetic elementary school tests with equal to 3% improvement in, say, Olympiad benchmark, which is kind of unintuitive. So what we do is a small modification where we're now considering relative performance against a reference model, where this reference model MREF is basically the same base model but trained on the full pool of data rather than subsample train set. So this basically shows how much of the performance could be recovered by training us on a specific subset with respect to this training on full data pool.
Right, and the full data pool here would be all the synthetic data?
Yes,
that was generated?
specifically 1.5.
1.5 billion samples of the synthetic data, and then you're gonna now come in and subset that synthetic data
Exactly.
using the gradient alignment.
Yeah.
Or the entropy of the gradients.
Yeah.
And then compare to that. Okay, got it, makes sense.
Yeah. So long story short, this is the results. I mean, it was very beautiful, right? The gradient entropy G-bandy is strongly predictive of how the model would generalize without actually having access to the test distribution. So the rank correlation is up to like 0.
And how much data was, that's what the N is here?
Yes. So we control for the scale of the data and see what the effect is.
So the biggest, the pink setting here, you're training on 1/15 of the total data.
1/15
in the
yes.
pool size.
Yes.
Okay.
And when you train 115, you don't epoch.
We did this using like a small validation set and to iterate until
So it could be the same amount of
it mostly is, yeah.
mostly the same amount of
Okay, we should assume, so let's just assume same amount of compute roughly.
Mhm.
Got it, makes sense.
So yeah, in both tasks, it's pretty consistent. And yeah, the performance here on the y-axis is the relative accuracy that I just described, but across 7 benchmarks in each of these tasks. Yeah, the interesting thing is diversity really matters even when we control for in this controlled setup, where we can see like even if we sample this subset from the same data pool, controlling for the scale, there's like up to 20% difference in how the model generalizes. You can also see the relationship between scale and diversity. So it's kind of beautiful because the diversity often could override the impact of scale because 10K subset of often outperforms 100K subset with less diversity.
So the data diversity score is through random data sets, like, or did you
So if you just randomly select subsets,
you get like
very similar scores.
okay.
Maybe because of the law of large numbers. So what we do is we use diverse kind of heuristic ways to sample subsets with spectrum of diversity. Like we do sometimes artificially sample low diversity subsets. Sometimes we do that with embedding similarity. Sometimes we just try to increase the diversity by picking, balanced sampling across the regions and stuff like that. And that's how we came up with all these
Each
points.
of the dot is a
Exactly. Yeah, I'm sorry, I didn't explain, but each of these points, x-axis is the diversity of that data set, and y-axis is the performance of the model trained on that data set. So each of these points are distinct data sets.
Is there any natural bound for data diversity score?
The G-bandy isn't.
There's no bound.
So it's just a positive score.
Okay, got it.
And it tends to increase, as you can see from the plot, when we increase the scale of the data, it tends to increase.
Yeah, that's what I think that was actually, like, I'm not sure how to articulate this question, but like, I'm trying to understand, like, why are these confounded? Like it seems like ideally, the data diversity score should be completely independent of the scale of the data set. Like, what is it about the data set size that is impacting it?
Yeah, I don't have a strong intuition to explain that, but maybe it's because of the nature of the entropy. Because like in entropy, if we have like it's easier. I think intuitively it's easier to get like rare samples when we have larger n compared to a smaller n. And when we are measuring the entropy, the rare samples impact is substantially larger, right? So maybe that's the reason why it tends to be in a higher scale.
Do you ever try computing the data diversity score over a fixed size subset of the given data sets?
Fixed size.
Like you would only compute, right now you compute the data diversity score based off of the size of this data set. So in this case, in the pink lines, you're computing it over 50K samples, whereas in the blue side, you're doing it over 10K samples.
Yeah.
Versus, well, I guess it would be the same. There would be a difference. Okay, well, never mind then, I guess.
Is there ever a drawback to increasing diversity? Like if you just look at performance on some single task that is like in distribution, do you see regression?
Yeah, so even in OD, like if we specifically latch onto one benchmark among all of these out of distribution benchmarks, then increasing diversity doesn't really guarantee improvements, right? Because you know, improving one benchmark performance, the best shot would be just making it in distribution. Like yeah, but our goal is to generally do better in average on these benchmarks. So yeah, it's kind of a tricky thing. But yeah, we also had this analysis on the distribution, as you can see here. And we see that increasing diversity oftentimes doesn't really improve that much on like in distribution. So yeah.
Oh,
Go
I'm
ahead.
wondering if you can, sorry, I wonder if you can do something like utilize like the mean as a way to improve the in distribution performance. So like the diversity is a measure of like your like the variance of the distribution.
Yes.
And I'm wondering if you can like match the mean somehow to like also improve the in distribution performance.
Mean, what would be the mean?
So like say that you have some like ground truth like examples for your downstream task. You
I
can have
see.
like the mean of the gradient of that, like match the mean of the like
Right.
the synthetic examples, but then also like account for like
Exactly.
entropy or something.
Yeah, I think so our setting, we kind of assume that we don't have any access to the target distribution information. So our basic assumption was that in that case, just increasing coverage of everything would be the good strategy. But if we have information to target distribution, I think matching the gradients would be. I think there are some literature on that as well. Like on average, matching the gradient dot product with the target distribution, increasing data of that kind actually lead to better performance on that benchmark. I think there are some literature on it, but yeah.
Actually, one other thing that I'm feeling is that okay, so when you're at 50K and there's another way to increase diversity is to add more points. And so if you go to 50 to 51K to 52K, rather than sub-selecting, you kind of go above the line. Like you kind of, I don't know how to put it together, but it's like a thought that you go like you cross that barrier by adding new samples. There's certain kind of diversity that you can get by adding new samples that you cannot get by sub-selecting. I don't know what that means. Like from 50 to 51K, you won't go on that line. You would start going on a line above, which is I don't know. I don't understand. Comprehend it yet, but there's a interesting thing happening here.
Yeah, maybe that also has to do with maybe the limitation of this might be that we are using some small set of strategies to sample these subsets. So with maybe more clever strategy, there could. I didn't really put that much of time in that because our goal is to evaluate measures themselves. But yeah, that's a good point. Good thing about this G-Bandy or Bandy score itself is that if you have an exact same data sets and we just aggregate them to double the size, the score stays the same. So yeah, the same exact copy paste doesn't really work to improve diversity, which makes sense. But yeah.
Wait, that doesn't make sense, right? Because then it means that because if you see over here in the data diversity score, if the size is 50K and the size is 100K, the performance is different.
But it's a different unique set of samples, right?
I think he's saying you take the exact same 50K and then just copy that.
And he says the diversity will remain the same.
Remain the
Right?
same in that
So
case.
the one way to make that 50K 100K is to copy that. And then it'll be 100K data set with the same.
All of these points are unique. Like the each of these points, the data sets, they have unique set of samples. So there's no duplicate in any of these things.
But that goes to what you were just getting at, which I think was a line that there's like this difference between adding new samples versus getting more data diversity out of out of the existing data set, which I think that's actually a controlled experiment to prove exactly what you're just suggesting. It says that adding new samples is different than just having more copies of the same samples.
Yeah, otherwise you would kind of
Otherwise it'd be
artificially
the
be able
same.
to go
Yeah,
up on the
yeah.
same score, right? But you don't.
But you don't.
This would also help with like data mixing experiments, right? If you were to put two data sets together and that increases the overall score, then you would expect it to do better overall.
Yeah.
Tons of questions.
That's a good thing, by the way.
Yeah. Yeah, regarding the duplicate, I think I have to think more about that, but yeah, let's just go for it now. Yeah, so our conclusion was that scale is the easiest way to improve in distribution. So yeah, you can see from these in two aspects. One, at each of the scale, the improvements from diversity with early saturation. And two, if you see these score numbers in the y-axis on each of these plots, the right one is the out of distribution we've seen from the earlier slide. You can see that the absolute numbers here are lower in the distribution. This means that, say for example, in the right plot in out of distribution, diverse 100K pink points could recover up to 80% of the performance of the full reference model, while in distribution performance, the same subsets, they only could recover up to 62% of what we could have achieved by training on full data. So yeah, just training on more data leads to better performance in industry. Yeah, so we also did a lot of comparisons with concurrent baselines using embeddings, as one of you asked, and some classic measures like n-gram stuff, perplexity and whatnot. There's one thing called skill set entropy, which uses LLM to kind of extract features, what kind of skill set is required to solve this math problem, and measuring entropy in that space. That leads to pretty much a decent performance, but it needs a good extractor. We use GPT-4 to extract those skill sets. So yeah. So yeah, there's the second part where now we have found in the earlier analysis, we have a good measure of that it's predicts how the model generalizes given this data. So yeah, once we have a good diversity measure, in case of synthetic data, we can improve the data quality by optimizing for that measure. So that's what we basically do here, using what is called prismatic synthesis. So it's pretty simple of a step where we iteratively cluster existing points in the gradient space, and then we generate new samples using LLMs, and then we do rejection sampling. So we do balance sampling, add only new samples that belong to sparse clusters in the current set. So it's a greedy maximization of entropy in the gradient space. Yeah, and here are the results of math reasoning where we train and compare against state-of-the-art data sets. We see that these baseline data sets usually take this approach. We collect some human-created problems and answers in, say, art of problem-solving form, and then we augment solutions using R1, 600, 700. Ours is much more crude than that because that was rushed. All problem solutions and answers are just generated by 32B and without any human annotation, of course. But yeah, you can see that it still outperforms SOTA baselines, SOTA data sets across the enterprise. Yeah.
I have a question. So to if you're gonna do like fine tuning of the Quen 2.57B, and I guess you used Quen 0.5 for the diversity score here as well.
Right.
Do you think there's a relationship there because there's the same family and that kind of correlates?
Yeah, that's the reason why we ablated the proxy model.
Mhm.
And even if you use Llama, I mean, we haven't trained model using prismatic synthesis based on Llama,
Right.
but the scores themselves are highly correlated with each other. So I think it'll be pretty much the same. Yeah. Yeah, we had the same thing on NLI as well. All labels in the baseline data sets are human verified, but we don't. So overall, strategic diversification of data, we offer larger gains. I mean, it's of course orthogonal to curation. Yeah, I have came up with some examples in NLI because it's easier to see intuitively, like what are similar ingredient space. And oftentimes you can see that they are radically different in terms of their topic or semantics. But if you actually try to solve these problems, you can see that they have some commonalities. So in this example is some set of examples from the same cluster ingredient space. You can see that in this case, the problems are asking about the understanding of membership. Like one of A is one of B's, A consists of B's, stuff like that. This case is about like membership of a person, someone lives in somewhere, someone works in some industry, stuff like that. As you can see, there aren't that many token overlap. Some cases include like stuff like this, where the location of the evidence is important, like, key information is at the beginning of the premise. You can see, like, since we're training these models to do NLI, like, these information could be included in the ingredient space, which is kind of hard to capture with embedding models that are not trained to do so, or a composition of different concepts. So yeah, here are some brief takeaways. Diversity matters, but it needs to be measured correctly. Off-the-shelf proxy model gradient information could be pretty much helpful in these tasks, at least for reasoning tasks. Task-specific metrics are quite limited. When conditions are the same, diversity has more to do with empirical generalization, while scale has more to do with distribution coverage. Prismatic synthesis allows us to improve generalization without knowing target distribution. So yeah, that's pretty much it. Thanks.
Really cool talk. So going back to your previous slide actually about the in-distribution and out-of-distribution thing, the summary slide actually.
Oh yeah.
But I was thinking this when you were mentioning the when you were giving the definition for data diversity, and I'm curious how you think about it. So out-of-distribution and generalization is such an interesting topic because it's something I did a lot of work on in the late 2010s. And then like I feel like largely the solution to out-of-distribution generalization has been make it so that nothing is out of distribution anymore, at least in pre-training, right? The solution has been train on everything. So now that creates this kind of interesting divergence between the setting of pre-training, where to some extent the goal is coverage over everything, versus say fine-tuning, where it is more about domain adaptation or things like that, where it makes more sense to have something OOD. So kind of given that, how would you adjust the way you frame this? Or the conclusions, and of course I understand that that's going to be speculating, but like, how do you think this differs in that context of pre-training, where the goal is just make everything in distribution, at least the goal could be, and that seems to be what it's
totally. Yeah, that's actually something that pierces through the center of all these narratives, I think. But I think my mental mode usually is that, although we do kind of talk about pre-training versus fine-tuning as if they are inherently different, like, I guess like it's, unless we're doing RL, like even RL, it's kind of different in terms of the data distribution. But I think in the end, it's not much of a different thing that we're actually doing, right? We're just doing maximum likelihood. It's just about some hyperparameter setups or the data distributions are different. And in that sense, the way we are kind of generating more data in less represented regions in the gradient space, and then training on that to improve the generalization, kind of also does a similar thing in terms of we're making this potentially insane fine-tuning sample to be in distribution to this model. So in that sense, I think it's nothing really too different. It's just that the source of the data could be widely different, and that in many of the times pre-training comes from the web, while in our case we want to just strategically focus on some specific regions, on specific tasks. So yeah.
So I think then like the takeaway you have here suggests that there's this difference between OOD and in-distribution and what you want. Like you want diversity for OOD, you want scale for in-distribution. So in the context of pre-training, where maybe this breaks down, how would you adjust this?
I see. Right. I haven't really thought about this setup in pre-training specifically, but if I were to distinguish between the two dimensions in terms of pre-training, I would say maybe oftentimes, maybe I'm just not well educated enough in this literature, but I don't think say the entropy of the data set is oftentimes the key dimension in when you're discussing about scaling laws. So thinking about how easy it is to kind of reach a specific entropy score by training on one data set and using that as a proxy of how diverse these samples are could be like one useful way of defining diversity outside scale. So I definitely think there is a huge impact on how diverse this pre-training set is in actual the model performance. So but it's I don't know why, but people aren't really measuring stuff like that. Maybe there are some probably different number of sources that we are actually sourcing the data for from stuff like that. But yeah, what do you think? It's all speculation.
I think my guess would be that this still kind of holds, except I would probably redefine like in distribution performance to be like the modes of kind of the standard distribution of pre-training data, and then out distribution really just being the tails in this case. So it's like I would still probably think that diversity helps. Like we found certainly that diversity helps with pre-training, and that was still true. But the reason it helps is a little different in that it's helping you to get coverage such that you are making more OOD stuff represented or OOD-ish stuff represented at a high enough rate that it starts to look in distribution.
Yeah.
But I don't know, that's also pretty hand wavy and speculative.
But I definitely I have a similar intuition when I was like kind of coming up with this idea as well, because in all distribution narratives, like all we want to do is increasing correct long tail regions in say the task space, right? So what we are caring about here in terms of generalization is some of these small underrepresented regions, but are in actual tasks and correct math problem and corresponding solution, but are kind of in a long tail, and we want to just amplify it. Yeah.
I was wondering for the in distribution math performance, if you start looking at performance after test time scaling, like PASAK, like sequential scaling or like parallel decoding, I'm wondering if you can actually see differences based on the diversity metric.
I see. That's actually a very good point. I have never tried it, so yeah, but I wonder what would happen. I don't have a strong intuition what could happen there. Yeah.
Like I feel like one of the main bottlenecks with parallel encoding or sequential scaling is that the model doesn't actually try different approaches, but just starts like
Fair enough.
rewarding the same thing. So I wonder if you can actually get like
Yeah.
significant boosting.
Right. True. The thing is, the way we are the dimension of diversity we're focusing on in this specific kind of synthesis way is like the problem side. Like we want to curate more diverse problems rather than having diverse solutions to one specific problem. Maybe so in that sense, maybe it's a little diluted, but yeah, that could be really the case. Yeah, thanks for that point.
So you said you did like some sort of like non-uniform sampling to get like this range of like diversity scores.
Yep.
Were there certain methods that worked really well if your goal is just to get the diverse data set out like efficiently? Like do you have like a recommended method of like essentially sampling from these pools to get the diverse, most diverse?
That was like a pain in the ass actually, like like having a good algorithm to do so. I think there are some max dispersion algorithms out there that I tried one or two of. They all do pretty much the same. So yeah, maybe I
Was that one of the ones that you got like the subset style with?
yeah,
Okay.
one of the algorithms. So yeah, I do have a little bit more of explanation of algorithms that are used in our appendix. So
Okay.
there are some references, but yeah, I was a little disappointed about those algorithmic literatures on how to choose subsets according to the scores. Like,
Sure.
Yeah, so I don't really have a good recommendation.
Okay.
Honestly.
So it seems like, you basically generate a large, like a superset of what you need, and then find that down based on, essentially like where the gradient space involves. Which, seems like it's extremely strong, but also like
inefficient.
Yes, like, is there? Have you thought about ways where you could just sort of more directly generate what you want, like condition on the
For sure.
samples that, like, preferentially condition on samples that fall in certain places in the gradient space, or like,
Definitely,
Yeah.
yeah. So I did had the exact same thing. The yield was pretty low, especially at the later stage where we already have generated a lot of samples. It's really hard to get the left representative ones. So one strategy I tried is exactly the thing you mentioned. Sampling few-shot samples exclusively from those left represented regions, and then prompt the model to generate something in that space, similar to these examples. But like grossly, it doesn't make too much of a difference. So yeah, it's kind of, maybe it has to do with the capacity of these data generator. I've only used as I said, the 32B or 2.572B to generate all of these. But with larger models, it might be more compute efficient actually to generate novel problems, I would say.
What is prompting strategy?
Sorry?
What is the prompting strategy?
It's just a few shot prompting. Like you have,
Like a random set of examples every time.
yes, that's the setup I finally chose to run. So
And so you're saying that you should find the samples which are in that region, that he
The
given X
normal.
was actually have high gradient, is still.
Yeah.
Could not, it did not really result in high gradient yield or something.
yeah, so yeah, the yield here is like the ratio of the samples that are actually in
Yeah.
like n% rare clustering. So yeah.
Actually, I wanted to see that table again where you compare with open source.
Oh yeah.
Figure out like.
Or
what they-
compared to OpenStack 3, we do worse.
Right.
Yeah.
So what are the sizes over here of these data sets, and like just to get a mental model of like.
The size of the data set?
Yeah, all of these.
So they are pretty much different. OpenR1 is 220K.
Okay.
OpenThinker is in the range of 100 to 200K. OpenThinker 2 is it's actually larger than ours, 1.14 million or something. Ours is exactly 1. R170 is just
And OpenThinker 3 is
it's I think 1.2 million or something.
similar.
It's around the
So if you computed the G20 score on 2 and 3, like would that inform why 3 is better than 2? Or
I think it's kind of tricky because like the way we have validated diversity measure is in a controlling for the quality and stuff like that. But when we are comparing two different data sets with completely different ecosystem, it's kind of there are a lot of confounders, right? So it could be more diverse, of course, but you can't really just say pinpoint that since this is higher in terms of G20, it will generalize better. There are a lot of
yeah, like the seed source, if it's same and you have subsamples, then the diversity measure.
I would say so, yeah.
Otherwise, like there are too many moving parts.
So I guess the biggest takeaway from G20 is the direction of improvements, because we now have a clear improvement direction, like how to improve the diversity, how to measure and improve it. But it's kind of hard to apple compare random data sets. And yeah.
A quick question, well, are there any failure modes using this score?
Right. Score itself is just a score, so maybe the failure modes could stem from how we're actually using it.
Right.
But yeah. So to the range of 1 million data generation, where we are trying to greedily maximize the performance. I mean the diversity. We didn't really find signs of over optimization, but I think there should be a limit to how actually improving entropy here could lead to improvements in actual model performance, right? So,
Sure.
But yeah, we haven't reached that point up to our experiments, so can't really tell robustly. Yeah.
Interesting.
Any other questions? But I can add one point that oftentimes like we do have a lot of different dimensions in terms of how our data would look like, right? So for example, one could be parameters. And Oftentimes those different dimensions are at odds against diversity, of course, because if you just want to maximize the diversity, then having completely gibberish solution would be the key. But it's kind of hard to balance those things.
Yeah, like trivial diversity, right?
Right, exactly. So that's that could be a model.
If you, so let's say that you didn't actually just to maximize out of the main performance. Let's say you knew ahead of time exactly what benchmarks you cared about. And there were basically no resource limits in this case. Like
No resource limits.
how would you just maximize number go up for a non-single benchmarks using that? Very curious. Because I feel like you put a lot of very valid constraints into it. But I like to think something's like, okay, like what if it has
Yeah. Well, if we have specific target benchmarks, can we use the same validation set?
Sure.
Just contaminate by using validation. If our sheer goal is to improve the numbers and we really give a shit about the future benchmarks coming out, then I would just generate with validation samples at the seed set, and yeah.
I mean, do you think how robust is this to throw forward? Because it seems like you still got improvements on other data sets by sort of optimizing for a single data set, and also got improvements on the data set you're optimizing for too, right?
Right. So when we're generating these, in the prismatic synthesis, we don't really have any a target validation benchmarks. It's just we have a seed set, which is actually the one of the rows, the open R1.
Yes.
And then all we do is just maximizing the. That's it. So we don't really have a target to work with in our case.
So I mean, do you think the results would just basically get better if these sort of if you just dump the more evals you got to sort of dump in and get the gradient, get the basically do the gradient clustering for? I guess what's to stop you from just eating every single eval and then generate essentially generating loads of synthetic data to maximize diversity across the largest possible eval space that you sort of create.
I see. Well,
And based on how well this generalized with one eval, do you think that would actually basically do you think you would overfit on that, or do you think you would just do even better to even more for even more unseen feature evals?
I guess in that hypothetical space, the biggest bottleneck could be the data generator, because they do have their own distinct distribution, and no matter how we're trying to improve the diversity, the support of that distribution we're generating from is limited. Right? We don't do any moderation to that. So I guess even if we do have a good objective, if it's hard for us to actually optimize for that, then I guess that's the limitation.
So then do you think because I feel one of the things you showed was that basically the generator doesn't actually matter as much as the diversity, right? Or am I mistaking? Was that the result of the proxy model?
Right, the proxy.
Okay, sorry.
I think if you use a stronger model, it will generally lead to better results. Over the goal.
Okay, so basically use the large, use a very large model, use an ensemble of very large models, and throw as many evals in.
Yet.
Cool.
Yeah.
Well, thank you.
Thank you so much. These are very novel.
Thanks.